Welcome back to the afternoon session of the Electrical Neuroimaging and Multimodal Integration training course of today. And just very briefly, before I give the word to Christian Bénard, we have a sheet of paper. If you are interested in the course material, in the slides, with additional handouts, we have models for dipole simulator. We will just collect all the material that we have and put it on a place where you can download it. Leave us your email address and we will keep you posted. It might take a week or two until we have this, but you will get all the information. I put this here, huh?
Okay, well, thank you, Thomas. Thank you for inviting me and to this workshop. So I'm going to present about the relationships between what we measure at the surface and what's being measured within the brain. And so there's this image of the iceberg, of course, as you know, that we only see the tip of the iceberg, and we're going to try to define how big is this hidden mass below the water. So as you know, EEG and MEG are surface recordings, and they are mainly sensitive to the synchronous activity of the pyramidal cells in the neocortex. And so we need synchronization of many cells to see something at the surface, and we need also the cells to be arranged in a nice, organized way. MEG and EEG differ by the influence of skull conductivity. MEG is much less, so magnetoencephalography, to those who don't know this electrophysiological tool. It has little influence of skull conductivity, because the magnetic fields, they go through the skull much more easily than the electrical fields. But it's not as good to see radial sources. So some remaining questions for MEG and EEG is the extent of cortex, which is necessary for seeing something at the surface, for recording something on the scalp level. Also, what is still a subject of debate is the influence of depth and, in particular, architectony, so the structure of the cortex on the detectability of the region. And it's especially crucial for deep regions such as hippocampus, amygdala, thalamus. So these structures are usually seen as a closed field, meaning that the field doesn't go very far away from the region because the organization is not as nice as the pyramidal cells of the neocortex. But as you'll see, there are some hope probably to see deep activity. Another important topic is the extent to which EEG and MEG can record high frequency activity, gamma band, or even higher, the ripples or fast ripple band. I'll present that in more details. Another important question is the accuracy of the inverse problem. So as you probably know, the inverse problem, so as a reminder, the inverse problem goes from the surface to the sources. As you know, it is an ill-posed mathematical problem, which requires hypotheses, strong hypotheses, to solve it, and they may not have a physiological background. So in particular, the minimum norm solution assumes that you have minimal energy of the sources, which may not be physiological. And there are, of course, imprecisions in the model. When you build the model of the head, you don't know precisely, as Scott was mentioning this morning, you don't know precisely the skull conductivity or whether you should add anisotropy of the tissues to take them into account. So, a way out of this, or interesting path to study these questions, is intracranial EEG, which is recorded inside the skull, so either on the surface of the brain or directly within the brain. This EEG is used during the presurgical evaluation of epilepsy as a second step after the non-invasive methods. So first we start with EEG and MEG and imaging, all kinds of non-invasive tools. And then in the second step, the neurologists decide where to put electrodes to actually study particular parts of the brain, to know what is the extent of brain tissues which need to be resected to render the patient seizure-free. And so all this is done on purely clinical background. This is done just for presurgical evaluation. But for us, for researchers, methodologists, it's a great opportunity to validate the non-invasive methods, as it gives some kind of ground truth recordings inside the brain. So I'll show you the different types, two main types of intracranial recordings. One of them is subdural grids. So this is a grid you actually put at the surface of the brain, and it records surface activity. That's very interesting because you can record quite a big extent of brain tissues. And this is the typical kind of activity we see in epilepsy. It's epileptic discharges, what we call often epileptic spikes. And you can see here that these discharges, which are spontaneous pathological discharges, they can involve only a few contacts or a large amount of contacts. So the amount of cortex which is involved in these discharges can be small or much larger. So another type of intracranial recording is stereotaxic EEG, or SEEG, which consists in placing electrodes directly within the brain. So here it's not anymore a surface recording, it's a depth recording. You go deep within the brain to reach medial structures. And typically, a patient would have between 5 and 10 electrodes, and each electrode has 5 to 15 contacts, which can explore hippocampus, amygdala, or lateral part of the cortex. So again, that's an example of signals where you see spiky discharges at the beginning of a seizure, and you see also high-frequency activity, which is the hallmark of the epileptic seizure. So first topic is the importance of the extent of activity. One of the pioneers on this question is Cooper, who used a very crude setup, but still very clever. He used a piece of plastic where he's punched holes, and he's put some source within a real skull, a wet skull, and he punched as many holes. He started punching a few holes and then more and more holes until he would see something at the surface. So it's a very crude method, but it gave an idea, an order of magnitude of the extent of cortex you need to see something at the surface. And he made this figure of 1 squared inch, so 6 squared centimeter, which are necessary to measure potential at the surface. And this figure of 1 squared inch stayed in the literature for many, many years. It was the reference, even though it's not exactly very plausible situation, but it stayed as a reference figure until some researchers have revisited this with subdural grids. And they recorded simultaneously these grids and EEG at the surface EEG and intracranial recordings. And they found that, in fact, it may be even bigger. The extent of cortex you need to see something at the surface, to see an epileptic discharge, is probably closer to 10 square centimeters. So you have to see it's really a big chunk of cortex which is active. This has been done also in MEG, and the figure they gave is lower, so it's good for MEG people, which I belong to. They claim that you need only 3 square centimeters to see something on the MEG, at least in this configuration, and we'll discuss that. The configuration is very important. Of course, you have to see this is on raw signals. On continuous signals, there is no averaging, and if you average signals based on some trigger, of course, you will increase the signal-to-noise ratio, and you may see smaller pieces of cortex. But still, it gives a starting point. This is a nice example of the impact of the source configuration, and to try to go beyond the fight between EEG and MEG. So these are sleep spindles recordings in simultaneous MEG and EEG recordings. And some spindles can be seen in both MEG and EEG, some only on EEG, and some only on MEG. So this is, I think, a very nice example that the two methods are complementary, and some activity will be well seen by a method and the other by another one. And this probably really depends on the configuration of the source. As I was saying, radial sources are not well seen in MEG, whereas on the contrary, EEG sees very well radial sources. Now I'm switching to the validation of source localization. So when we want to go beyond the surface recordings and actually localize activity within the brain. And again, this is examples from epilepsy, obviously, as we're recording patients. That's an early paper by Isabelle Merlet and Jean Gottman. They recorded a 28 scalp EEG, and during SEEG, only a few scalp EEG for matching the activity between the depth and surface. And they modeled with equivalent dipoles. So that's one very standard way of localizing the sources of the epileptic spikes. So you see here the location of the equivalent dipole to epileptic activity, and a marker of where it was recording in SEEG. So you see the SEEG electrode, and so the contact is right there. So that shows that there is a very good match between the localization made non-invasively and the actual invasive recording. And on average, she observed that the distance between the dipole and the main SEEG contact, so the contact in intracerebral contacts with a higher amount of activity, was 11 millimeters. So to us, by clinical standard, this is extremely good because the surgeon is not going to remove a few millimeters. He always removes big chunks of cortex. So 11 millimeters, we can live with that. She also conferred propagation patterns, and what she observed is that activity from focal sources were not visible. So again, we need at least a big piece of cortex to see it at the surface. So she had the figure of 8 intracerebral contacts. This is a study from our group, from Martine Gavaret, in temporal lobe epilepsy. And Martine has classified patients depending on the distribution of activity seen intracerebrally. Some patients had only lateral epileptic discharges, so meaning from surface cortex, so either the temporal pole or the lateral part of the temporal lobe. So there was these lateral patients, mediotemporal patients that have activity both in the hippocampus, amygdala, and the lateral regions, and patients with only medial activity. And what she observed is that patients with purely medial activity, there was no activity visible at the surface. So the activity is either too deep or likely in regions where the architectony is not suited to have fields that propagate. But then when you have activity which is visible, so the lateral activity, it can be localized with a very good precision. That's another example in frontal epilepsy, so pathological activity in the frontal cortex. And she made different cases, she studied different cases. Here you have an example of the anterior cingulate, which is presenting epileptic discharges. And this was very well localized. So you see here, maybe it's not very clear, it's yellow dots indicate where the epileptic spikes were recorded. So this is where it was recorded intracerebrally, and this is the non-invasive localization. So the localization is excellent. Now, on other parts, it could be more complicated. In the orbitofrontal parts, you see that there is an extended activity in the orbitofrontal regions that can be seen with SEEG. But the non-invasive localization, the source localization, only sees the lateral part. So here you see a mismatch. We see only part of the iceberg. So architectony seems to be probably more important than depth. This is a case study of a bilateral occipital sources. So, of course, we like to show it because and I'm seeing Christophe entering. We like to show this example that MEG gives very good results compared to EG. But, of course, an EG person will show the reverse cases where EG sees better. But in this very particular case of bilateral occipital sources, two sources that are symmetric but very close to the midline, they can be very well distinguished by MEG because of the properties of the magnetic fields, whereas EEG sees only one big blob. And you can also trace the propagation of activity from one side to the other, which is seen also in intracerebral recordings. This is a study from the Swiss group, where they compared the spiking regions, so the so-called irritative zone, and the seizure onset zone. So this is going one step further and trying to ask the question, how clinically relevant this is all. So they studied a large cohort of patients, 38 patients with subdural grids, and also a very large coverage of EEG with 64 to 128 channels. And they measured a median distance of the EEG source with the most active grid points of 15 millimeters. So again, this is very good. And somehow surprisingly, but very important, very nice to know that they didn't observe any difference in accuracy between temporal lobe or extratemporal epilepsy. We always wonder if temporal lobe epilepsies are not more complicated because they have this deep activity, but they didn't find a difference. And also, they found a good prediction of the seizure onset zone based only on activity outside of seizures. So this is a very good news clinically. This is a study of our group where we tried to go beyond a single source and try to see how different sources interact. So we extracted the networks, the epileptic networks from the MEG data with independent component analysis that was presented this morning by Scott. And we defined the epileptic components. So visually, based on the topography of the components and based also on the activity seen on the traces, we identified components with a nice topography which indicates a cerebral source, a nice dipolar topography, and epileptic spikes. And then we studied the interaction between these components. So you see that sometimes there is a spike only in one component, sometimes it propagates, it interacts with the other components. So there is actually a network of activity visible in these discharges. And this is the work of Ursula Malinowska. And we did a representation, a 3D representation of the networks that were extracted from the surface. So this is a non-invasive extraction of networks based on ICA. So these are the sources of ICA components, and the directionality is given by the timing between the sources, between the discharges. And we defined a leading region, which is the region from which the activity originates. And then we compared that with intracerebral networks built only on intracerebral activity. And again, we defined the leader. So you can see that the MEG sees only part of the network, but it sees the important part. You see where the leader of this network is very well localized by MEG. The differences is really minimal. So there is a very good match here between the surface data and the intracerebral data. But of course, it's not as simple as that. And we have a case also where we identify a plausible network and what is identified as a leader on MEG is actually only a node of the network on intracerebral data. The leader in intracerebral data is here. So this seems to indicate that this wasn't seen by MEG. So now that's an example of a case where MEG doesn't see the important part. And what we localize with MEG is sensible because it's a part of the network. So it exists. It doesn't invent something, but it's not the most important part. So one always has to see this data with caution, a lot of caution. So all what I presented so far are separate recordings. People recorded MEG, EEG on one session and intracerebral EEG in another session. But there are strong limitations of these separate recordings, because they do not warrant seeing the exact same activity. There are, as you know, fluctuation in activity due to the state of vigilance, maybe also to the level of medication of these patients. And also, very importantly, separate recordings do not permit to use the inter-event fluctuations, so what we would call single trial fluctuations, as a source of information on the relations between the signals. So you may know the literature of EEG fMRI. There was a big advances in EEG fMRI analysis when it went to single trial analysis. We want to see the coupling of the signals on the actual same data. So not separate sessions, the same data seen both at the surface and at the depth. So this is an early recording by Alarcon of a subdural electrode, so that's still yet another way of recording intracranially. So it's one electrode and scalp EEG. And this is the foramen ovale recording, so right below the temporal lobe. And what they've shown is that surface activity sees only the propagation. You may see here the very early spiky stuff is very focal, very deep, and is not seen at the surface. So it's only when the activity starts to propagate and involve a larger extent of cortex that it starts to be visible at the surface. This is studied by Gore and Lance, also one of the earlier studies of simultaneous EEG and intracranial EEG. So this is 22 scalp EEG along with subdural electrodes and source localization. And what they studied is whether the sources could be distinguished at the sublobar level. So sublobar means we can distinguish between the medial and the lateral part here, or the anterior or posterior part of the lateral temporal region. So this means we want to test, they wanted to test whether they could really distinguish subparts of the brain. Not only globally say this is temporal lobe epilepsy or frontal epilepsy, but can we really tailor the surgery to go to a specific brain regions? And they actually shown very nicely that you can. And surprisingly, also for mesial sources could be distinguished from more lateral sources. One of the first recordings here by Santuste of MEG and intracerebral EEG. That was only one SEEG electrode and simultaneous MEG. And they tested whether the epileptic discharges could be seen at the surface. So they detected independently epileptic spikes at the surface and at the depth. And they saw that when it was neocortical spikes, one could detect 95% of the spike, whether only 25 to 60% of the spikes from the mesial structure could be detected. So this is half-empty glass. It's still pretty good, 25 to 60%, but it's not as good as neocortical activity. This is a study we did in our lab. This is the work of Anne-Sophie Dubarry. And we wanted to go beyond EEG, SEEG, or on one hand, or MEG, SEEG, and we wanted to record the three modalities simultaneously. So to our knowledge, it is the first attempt to do that. So you see the patient here in the MEG with the wires coming out with both SEEG and EEG sensors. And Anne-Sophie recorded activity from a checkerboard stimulation. So this is a feasibility study to see the quality of the signals. And she observed very nice evoked potentials on the three modalities all together. So this is, again, this is all recorded all at the same time. You have the evoked potential in SEEG, in EEG, and in MEG. And to go beyond that, we wanted to go to test whether we could go to single trial analysis, because to really extract all the information from the simultaneous recordings, we want to have them really at the level of a single event. And this is the raster plot of the three modalities, and very nicely we can see that the activity can be recovered, so the visual evoked potential can be seen on the three modalities at the single trial level, and correlations are observed between EEG, SEEG, or MEG, SEEG at the time of the evoked potential. So that means we have a tool now to study the links between depth and surface at the single trial level. And Anne-Sophie has a poster on the continuation of this topic on SEEG in language protocol. So another application of that is a test we did to compare ICA and beamformer. So we were wondering of the differences between these two methods for localizing the sources of epileptic activity. So this is an ICA component recovered from MEG, and this is the result of a beamforming and actually doing spike detection of epileptic spikes on the beamformer, on the virtual electrodes. So this is an approach which is based on source localization, on the lead field matrix. And this is an approach which is based on finding independent components, so based on a statistical criteria. So two different criteria for defining a spatial filter. And this is an example of spikes, average spikes we see on ICA. And the fact we had simultaneous recordings means we could see which contacts are involved during the epileptic spikes. And very nicely, we see that we have SEEG contacts which have significant activity during the spike detected at the surface, and that it is in the right region. So in red here, you have the SEEG contacts activated during the discharge, and in green, you have the source localization of these two methods, which are the same. So in a focal case, when there is one source, this source can be very well extracted by either ICA or beamformer. It doesn't really make a difference. So now we're going to more challenging situations, deep activity or high frequencies. So the deep structures, there are some reports, a few reports, that you can actually measure hippocampus activity with surface MEG. So this is Sarang Dalal's data showing that you can reconstruct theta activity from the surface that has zero lag with the hippocampus. So it's not a proof, but it's a good indication that it's seeing the same activity. Of course, it could be zero lag with propagated activity, but still it's very encouraging that MEG could actually see the hippocampus activity. Another report by Sylvain Baillet, he compared a virtual electrode reconstruction in the mesial region and the actual SEG recording performed within the hippocampus. And the two traces are very similar. So reconstructed from the surface or recorded directly within the brain. Some people have tried to do the reverse way, so to mark activities in the depth and then to see how it reflects at the surface. So again, this is hippocampus activity, hippocampus spikes. And the averaging is performed based on the hippocampus, the SEG hippocampus spikes. And one can observe, once you know that it happens in SEG, you can see it on the average at the surface. And it can allow us to measure the amplitude that is visible at the surface. So it's a small amplitude. It's 5 to 10 microvolts, but still not non-zero. There is some activity propagates from the hippocampus to the surface. Another very nice study by Laurent Kessler, a recent study, where they did similar things, but with more SEG contacts. And what was very important here is that they had contacts in very close by regions, which are neocortical. So the basal parts, lateral part, or pole, temporal pole, to be able to really say that the spike is within the hippocampus only, and it's not a propagated activity. And again, they see a very small amplitude at the surface, so which is consistent, 7 microvolts. And it's actually a signal-to-noise ratio which is negative. So on raw signals, you cannot see it. So you would need further processing to see it. There are also very interesting new paths to try to reconstruct this hidden activity. One is to improve the models we have. So this is a biophysical model of hippocampus and amygdala, which is put in the source localization model. You actually explicitly model these structures to reconstruct activity coming from them. And another interesting path is computational modeling, because in a computational model, you can add hidden variables. So a region that you don't observe, but which is actually put into your model, you can try to infer the parameters from this region. So this is a study, again, by Attal. Olivier David also worked on that, to try to estimate the activity of, for example, of thalamus. Even though you cannot record the thalamus from the surface, or very unlikely, you can still estimate the thalamic activity from these models. Now, in terms of high-frequency oscillations, there is a report in 2010 of simultaneous subdural and MEG data, which shows that high gamma activity can be well seen on MEG. So that's actually a very nice, very good news, that we can see not only low gamma, this we knew, but also high gamma. So this is the high gamma discharges, and it's very well visible at the surface. And there's a report on EEG by the group of Jean Gottman, Rina Zellman, with, again, simultaneous recordings, simultaneous ECOG and EEG. And she could observe ripples and fast ripples. So this is going even higher in frequencies, between 100 and 300, which could be seen at the surface. So this is very surprising. I mean, it was, again, very good news that we could see such high frequencies at the surface. And I mean, it's a race now, it's a competition to go as high as possible in frequency, and there's even higher frequencies that have been reported very recently, 900 hertz or even above 1 kilohertz. So to me, this is extremely surprising. I didn't know that things could happen at this frequency, but that's a new venue for investigations. So this is all expanding the range of what we can see non-invasively. We can really push the methods to go to higher frequencies. So in conclusion, the take-home message would be that intracerebral recordings confirm surface recordings in a large proportion of cases. So we confirm the intracerebral recordings confirm that it's useful tools clinically or in basic research. The main sources we will see are neocortical sources with sufficient extent, which of course a signal-to-noise ratio which increases leveraging. And in some favorable cases, deep structures can be observed, such as hippocampus. Of course, intracerebral activity keeps a higher sensitivity because we're really within the brain or on top of the brain. And MEG-GC is only the tip of the iceberg, but maybe it's the nice part of it still, when it becomes really synchronous. And this can be surely improved by signal processing methods and modeling, so ICA, source localization, biophysical modeling, computational modeling. And we think that simultaneous recordings and all the kinds of computational biophysical modeling, they could improve the understanding of the signals and define the best strategies to be used. So this is still an active path of research. So thank you very much. I hope this workshop will help you to surf the iceberg being in Hawaii. Thank you so much. Do you have questions? No one wants to surf. Okay. Everything was clear. Maybe one, yeah.
Thank you for the presentation. I'm very interested in comparing the CEG network with the reconstructed network from the MEG or the EEG.
Yes.
How finally you compare both networks? How do you compare nexus? Which kind of parameters you use?
Yeah, it's a very good question. It's a tricky one. We did it quite grossly. I mean, we defined the regions that were involved. So with again, to use the terms of Goran Lenz, a sublobar division. So we did a division of the brain and we checked whether the nodes of the network were in similar regions. But I think what you allude to is that it's difficult to compare networks. It's actually, if you want to do it to quantify differences between networks obtained with two modalities, it's a tricky thing. So we did it in a very raw manner. But recently, methods have been proposed to try to quantify that based on the strength of the link and on the nodes. You have two things you can compare, is the link and the node locations.
Yes, exactly.
So you need a measure that incorporates the two. So
yes,
at least
yes.
Sylvain Taquecard has, in Marseille, had proposed a metric to do that.
Exactly, and also there is some new algorithm to compare graph similarity, taking into account the physical location of nodes and the edges, and I think it could be also
exactly
interesting.
Yes, definitely. You're welcome. Okay, well then, thanks again. Next speaker.